All right, so starting with 5.3 today, independence and the multiplication rule. Two events are independent if the occurrence of one event does not affect the other. Then two events are dependent if the occurrence of one event does affect the other. All right, well, you guys copy that. I'll take the sweatshirt off. Give me a second.
I like your sweater.
Oh, yeah, champions,
Yeah, oh, that's great.
I'm a little concerned about AD right now, but we'll see.
I just think it's weird that they started so fast up after they won the championship, and then it was like right back to it. So it was like,
Yeah, that just goes to show you money talks.
yeah, I know, literally. Now we got people all up in the stands. It's like, hey, I'd like to go to school. Just saying.
All right. Anybody? Of course, if I ever scroll up too fast, you guys let me know. So the first exercise, independent or not. Get that bar a little better. Where's my blue? There we go. Independent or not. So suppose you flip a coin and roll a die. Are the events obtain a head and roll a 5 independent? So are they independent events? So I already wrote the answer down there, but yes, they are independent. One has nothing to do with the other. So the fact that you rolled a die has nothing to do with you flipping a coin to get heads or tails. So those are two separate events. Neither one of those affect the probability of the other one occurring. All right. Are the events earned a bachelor's degree and earn more than $100,000 per year independent? All right. The answer is no. Even though you don't need a bachelor's degree to earn $100,000, but earning a bachelor's degree increases your chance at earning $100,000 or more. Remember, that's what we're talking about, probability. The probability of earning $100,000 or more, the chances of doing that, or the probability of doing that, is increased with a degree. All right, any questions?
No, but I am noticing that the section 5.3, 5.4 are super like quick, like 5 questions or
Mm-hmm. Yep. Mhm. All right, so the multiplication rule for independent events. Event E and event F are independent. If that is the case, and you want to know what's the probability of both of them occurring, then you would just take the probability of each one of them individually and multiply them together. All right. So in the game of roulette, the wheel has slots numbered 0, 00, and 1 through 36. A metal ball rolls around a wheel until it falls into one of the numbered slots. What is the probability that the ball will land in the slot numbered 17 two times in a row? I'll give you a chance to write it for those who are writing. right. So these events are independent. So, in order for us to use the multiplication rule of independent events, you have to establish that these events are independent first, right? So these events are independent. The occurrence of rolling the ball, rolling 17 does not affect rolling 17 again. So, if it hit 17, it's not like there will be a blocker on the 17 slot to stop you from rolling 17. So if the fact that it rolls 17 the first time has nothing to do with the fact that it will roll 17 the second time, right? Get a clear wheel. So remember, whenever we're trying to establish our probability or find the probability, we have to establish a sample space. So our sample space is going to be 38. There are 38 numbers. Remember, there's 0, double 0, and then 1 through 36. So there are 38 numbers. There's only one number 17. So it's one number in our event. And the probability is 1 over 38. That's the probability of getting a 17 is 1 over 38. All right. Questions? Any questions? So now we don't want to know what's the probability of rolling 17. We want to know what's the probability of rolling 17 twice in a row, basically. So I want to know the probability of rolling 17 and then 17 again. We found the probability of rolling 17 once. So it's 1 over 38 times 1 over 38. And my math lab will let you know how they want to answer, if they want it in decimal or if they want it in fraction. Both of those answers would fit that.
Okay, so I'm just multiplying 38 times 38 to get that down there, and then I'm dividing one, or hold on, I lost myself.
All right.
So 38 times 38, and then I got my 1444, whatever.
Mm-hmm.
And then to get the 0006925, what am I multiplying for that, or what am I, you know what I mean?
No, you would put, well, unless you want to do it by hand, but you would do 1 divided by 1444 in the calculator.
Okay.
And that should give you that decimal value.
Okay, we're on the right track, you guys. All right.
All right. Anybody else before we go to the next one? All right. So the probability that a randomly selected 24-year-old male will survive the year is 0.9986, according to the National Vital Statistics report. What is the probability that 3 randomly selected 24-year-old males will survive the year? And then what is the probability that 20 randomly selected 24-year-old males will survive the year? All right. So when we go to answer these questions, remember the first thing we want to know, are these events independent? And in this case, the answer is yes, because the fact that one 24-year-old lives has nothing to do with another 24-year-old living. So yes, the events are independent of each other. The probability that a 24-year-old male will survive is 0.9986. We got that from the problem. And we want to know what's the probability that 3 randomly selected 24-year-old males survive throughout the year. And since they are independent, all we're doing is multiplying those 3 probabilities together. And we have this number right here, 0.9958. So also just make sure you know how to use your calculator. You know, I was emphasizing that symbol right there lets you raise it to the third power. And there are different buttons. You might have the cubic, button on your calculator, or you may have something like this where they let you put a number in the bottom in the base and then a number up here for your exponent. So different calculators have different functions and different buttons for you to be able to perform this task. So just make sure you know how to use your calculator. And if you don't and you have questions, always feel free to ask. All right. Questions on A.
Not so far, no.
All right. So B was, what is the probability that 20 randomly selected 24-year-old males will survive the year? So we'll take that 0.9986 and raise it to the 20th power, and that'll be 0.9724. All right. Questions? Any questions? All right. Next one. Compute the probability that at least one male out of 100 24-year-old males will die during the course of the year if the probability that a randomly selected 24-year-old male survives the year is 0.9986. So still leaning on the information from the last problem. Give you a chance to write. All right, so we want to know what's the probability of at least, where it go? I lost my spot. Yep, there you go. It's up top. I'm looking down bottom. So we want to know the probability of at least one male out of 1,000 will die. Now, the probability that we have is the probability that a male will survive. So we're going to have to use the complement rule. In other words, we're looking at the probability that at least one dies. Now, what we can do is calculate the probability that none die and then subtract that from one, because here we're looking at least one die. So the opposite of at least one dying is none dying. And we talked about a complement rule last class when you subtract the opposite from one and get the probability of the rest. So we take 0.9986, raise it to the 1,000 power, because that's what we're talking about, at least one male out of 1,000. So 0.2464 is the probability that none will die. If you chose 1,000 24-year-old males, the probability that none of them will die throughout the year is 0.2464. Now subtract that from one. The probability is 0.7536 that at least one of those 1,000 will die.
Wait, how'd you get the 0.2464 again?
Raise this to the 1,000 power.
Oh yeah, okay.
Yeah, so that's all calculator work. Unless you're just real nice with it, that's all calculator. So so you're just talking about taking 0.9986 and you can use that symbol in the calculator to raise it to the 1,000 power. All right. All right, questions on 5.3, like your classmate mentioned, 5.3 and 5.4 are relatively short. So questions on anything I mentioned in 5.3 before we look at 5.4?
No, pretty good.
Mm-hmm.
But yeah, definitely short though, because I was following along with the homework too.
Mm-hmm.
Yeah. I think it's like 5 or 6 questions. Something like that.
Yeah. Well, let me do something real quick. Notate this section or this set of notes. I 5.3 in there. I didn't do that. All right. So let's look at 5.4. Conditional probability and the general multiplication rule. All right. So conditional probability. Notice the notation here is F, and then they have this straight line, and then E. That's the probability that F occurs given that E has already occurred. So that's your conditional probability, the probability that F occurs given that E has already occurred. So now we're talking about dependent events. The fact that E has happened affects the probability of F happening. Remember the last thing we were looking at, last section, we were looking at independent events. Those events have nothing to do with each other, nothing to do with the probability of the other one occurring, but that's not here. In this section, we're looking at dependent events. The fact that one event occurred affects the probability of another event occurring. All right. So once again, we look at the notation, F slash E or F line E, whichever way you want to call it. I don't even know if I need to look up and see if there's a name for that. I don't even think I know if there is one. Other than that, it's a line. So F line E means the probability that F occurs given that E has already occurred. So the positioning of F and E matters, because if you flip it, you're talking about the probability of E occurring given that F has already occurred. So just throwing that out there. And then that also will play a role in how you calculate it. So you have E and F on top, probability of E and F on top over the probability of E, or the number of E and F on top over the number of E. All right. So the first example we have, let me erase some of this. We have the marital status of males and females 15 years or older in the US, and it is in millions. So I'll give you a chance to write down that chart. We got never married, married, widowed, divorced, and separated. Then on top, you see we have male, female, and totals. Also have totals on the other one. All right. So use the table to answer the following.
Wait, hold up. Could you go back to the chart one more time? I was almost done.
Not a problem.
Thank you.
Not a problem. All right. So answer the following by using the chart. First, they ask us to compute the probability that a randomly selected individual has never married, given the individual is male. Then they want us to do the opposite in the next one. Compute the probability that a randomly selected individual is male, given the individual has never married. So I'll give you a chance to copy that. And we'll do the problem. So looking at A, we want to compute the probability that a randomly selected individual has never married given the individual was married. Given the individual was male, can't be never married, given that she was already married, right? So I'm going to let N represent never married, M represent male. So that means as far as the formula is concerned, I need the number of individuals that was never married and male, and then the number of total males. So remember what this symbolism, oh, still got my eraser. Oh, this symbolism right here means the probability that the individual chosen is never married, given the probability, the person is male. So never married and male is right here at 41.6. And then the total number of males is 1 in 22.5. So there you go right here, 41.6 over 122.5. And my math lab will let you know how many decimal places to go out and all the good stuff like that. Where we have 0.34 as our answer. The next one, and you do this exercise just to show you the difference. That, you know, if you were to flip the letters or flip the events, that you will not get the same probability. So the next one is the probability that that you chose a person that is male, given that they were never married. So we're looking at the probability of, or the number of someone being male and never married over the total number of never married people. So you go back to your chart. So now you're looking at, well, male and never married is still the same number, but then you're looking at the total number of people that never married, which is 78.5. So that's the 41.6 over the 78.5. Divide that out, that'll give you 0.53. And so that's all that they're asking of you in this example. Any questions? Mm-mm-mm. All right. Scroll up is okay. All right. So the next one, suppose that 12.7% of all births are preterm. Also 0.22% of all births resulted in a preterm baby who weighed 8 pounds, 13 ounces or more. What is the probability that a randomly selected baby weighs 8 pounds, 13 ounces or more, given the baby is preterm? And then, is this unusual? All right. So I'm going to call W, event W, weighs 8 pounds, 13 ounces or more. And then P for preterm. So the probability of getting a preterm or having a baby that's preterm is going to be 12.7%. That's what they gave us. So convert that to a decimal, that's 0.127. Probability of being preterm and weighing 8 pounds, 13 ounces or more is 0.22%. So as a decimal, that's 0.0022. So you just move your decimal to the place to the left 2 places, just like with a 12.7%. So we want to know what's the probability of getting a baby that weighs 18 pounds. I say 18 pounds, gracious. 8 pounds, 13 ounces or more, given that the baby was preterm. So the way we calculate that is we look at the probability of P and W, or the probability of P. So we have both of those pieces. So that's 0.0022 over 0.127. And so that's going to be 0.0173. And that's 1.73%. You know, if my math lab asks, well, I believe they want it in a decimal form, not percentage, but either one of them should be fine. So questions on that before we look at whether it is unusual or not.
So far, so good.
All right. So now the question is it unusual or not? Remember, we had a marker that would dictate whether it would be unusual or not. There was a percentage. If it's lower than that percentage, then it is unusual. And so, yes, it is unusual because the probability is less than 5%. Remember, that was our marker that we were going to use to determine whether a probability is unusual or not. 5% is going to be that for us. So if it's less than 5%, then it is considered unusual. All right, questions? Any questions? All right, so your general multiplication rule, if you want to know the probability of E and F, and they are dependent events, remember we did this before, the multiplication rule for independent events, but if they are dependent events, then the probability is going to be the calculated probability will do the probability of E times the probability of F, given that E has already occurred. All right. All right, so the probability that a driver who is speeding gets pulled over is 0.8. The probability that a driver gets a ticket, given that he or she is pulled over, is 0.9. What is the probability that a randomly selected driver who is speeding gets pulled over and gets a ticket? All right, so I'm going to call T for gets a ticket, P for getting pulled over. So it told us the probability of getting pulled over is 0.8. And then the probability of getting a ticket, given that you were pulled over, is 0.9. All right, so the probability of a driver who is who is speeding and getting pulled over and gets a ticket, we calculate this way according to our multiplication rule. The probability of P and T is probability of P times the probability of T, given that P has already occurred. So you get pulled over, and then what's the probability of getting a ticket? The fact, given that you got pulled over. that's going to be 0.72. All right, any problems? All right, I think we have, is it one more? Let's see. Yep, this is the last one for today. All right, so in a study to determine preferences for self are more or less prevalent than preferences for others. Researchers asked individuals to identify the person who is most valuable and likable to you, or your favorite other. Of 1,519 individuals surveyed, 42 had chosen themselves. I'll give you a chance to write that. All right. So A is suppose we randomly select one out of the 1519 individuals, 1,519 individuals. What is the probability that he or she had chosen self as a favorite other? All right. So we want to know what's the probability that someone has chosen self as a favorite other. Once again, whenever you're dealing with probability, you want to establish your sample space. You know, we have 1,519 people to choose from. 42 of them chose self. And so the probability that's picking someone that chose self is going to be 42 over the 1,519. All right. So from there, if two individuals from this group are randomly selected, what is the probability that both chose self? So here we have to be careful. You know, we want the probability that the first person I choose chose self and the second person I choose chose self. So first is the probability that the first person I chose self. Then second, the probability that the second person I chose self, given that the first person I chose self. I know it sounds funny, but we have to consider the first probability is 42 over the 1,519. So remember that. But then the second one, you would have to take one away from each number. Okay. Well, first of all, if I chose one in the first from the first group right here, that means there are no longer 1,519 people. There's 1,518 people now. And if one of those were out of this 42, so there's no longer 42 people left, there are 41 left of that category of people. So that's why we had to go down one in both categories. All right. Make sure we're okay with that. This was the original probability of if I would have chose randomly out of the 1,519 people, 42 people of them chose self. So if I wanted to know the probability of choosing one of those people, it's 42 out of the 1,519. Now, if I take that person out of the group, this number is no longer the same. It's 1,518. And then out of that 1,518, if I took one out of the 42, then there's only 41 left of the people that chose self. So that's why we have our different probabilities there. All right. So once you establish that, and I probably should have a parentheses right here like that. Probably erased it by mistake. So then you go ahead and multiply those together, and you get this number right here. Question. And in the green, it was just, if you wanted to convert it to decimals first, it was just, somebody probably asked a question about what were the decimal was. So that's why I put that there. But all you need to do was the 42 over the 1,519 times the 41 over the 1,518, and that will give you your answer. All right, questions? Any questions?
No, I'm sure once I get into 5.4 homework, I'll have some questions for next class.
Okay. Okay, not a problem, not a problem. Last one, compute the probability of a randomly selecting two individuals from this group who selected self, assuming independence. So remember, if they are independent, that's the key word here. If they're independent, that means one probability does not affect the other probability. Those two events have nothing to do with each other. So the probability of getting someone who chose self is 42 out of the 1519. But if they're independent, that probability will still be the same for the second group. Evidently we're doing replacement, or we're putting that person back in the group to choose from. But either way, the probability will be the same, 42 over that 1519, because they're independent events, independent probabilities. So multiply them together, and you have your value, 0.0007645. All right. Any questions?
No, I appreciate your time though, for sure.
Yeah, not a problem, not a problem. Not a problem. Appreciate you guys coming through. I could be teaching to a blank screen, so.
I know. I always feel so bad. Like I feel bad. Sometimes I'm like, maybe I'll just come to class for one day for real. I don't know. Then I get all like weird and nervous. I don't know. Last semester I felt all weird. Like everyone was in my room and stuff. I was like, oh my God.
Yeah. Well, this might be the last semester that we'll be doing this. I think for the summer, it's still doing the same thing because there was, there's no real plan in place to just come back. But, hopefully with the vaccine and everything that's going down,
I know.
the fall we'll be back to business as usual. I'm kind of comfortable doing this now, so I'm messing around, getting me my flow. I may not want to go back to work, so.
I know, but I think I'd be excited for it though, to be honest, because I'm tired of the computer and stuff. Like,
Yeah.
I don't even know who's in my class. Like, I want to know that and stuff. So,
like. Yeah, and sitting at a computer all day sometimes, wears on your eyes, make your head hurt.
and your
tough.
back and stuff. You're like, dude, all right.
Yeah, and that was my exercise, so I weigh more now than I've ever weighed before in my life.
No way, dude! You look good. What are you talking about?
Well, I'm not like, I'm not like, super heavy, but I'm just saying I'm heavier than I've ever been before in my life. You know what I mean? So
I think everyone's on the same page. Okay, pretty sure. Like,
yeah.
Almost positive.
So I guess I'll get off of that. So with that being said, me and my heaviness. Next class, that's it for chapter 5. So next class, I'll open the floor for questions before we do anything else. And we'll go from there.
Sounds good. You guys have a good rest of your day.
All right, thank you. You do the
All right.
same. Do I still have to show you my first homework? Now don't forget, if you never turned in your definition, chapter 1 and chapter 2, you don't want zeros for them,
Right.
if that's what you mean by your first homework. But as far as scratch work, remember, you don't ever have to show me any scratch work for your homework. Just scratch work for tests, the ones that call for calculation. Remember, the first one was definition, so we really didn't need scratch work for that. But
Right.
we start talking about your test, then you would show scratch work for your test.
Okay.
Yep.
Kind of just send over a picture of it and kind of stuff like that.
Yep, not a problem.
Okay.
The first assignment that you couldn't open, yeah. So yep. Don't forget we got assignment 1 and assignment 2.
Right.
If I don't have you down for them, to make sure you send them to me so I can put you down, get your grade in. If I said I got it and I didn't put your grade in yet, always feel free to shoot me an email to remind me. Because I think I put down everybody that I said I got it or responded to your email.
Yeah.
If I responded to your email and you don't see a grade for it, then go ahead and shoot me that reminder so I can check and see why I didn't do it. I might have just missed it, but yep.
You said that you couldn't open my my pictures or like
Mhm.
everything that I sent. So you said to wait till after class and show.
Okay, yep.
You?
So we can do that. So of course you would have to let me go ahead and stop the recording.
Yeah.
Okay. All right.